We finished this slide, I know, 9 and 10. In fact, there was a question in the exam. I just wanted to make sure, double ensure that you guys understood this part. You see, the problem is that when you have these virtual machines and they have the NICs, some of them be part of some multicast traffic, right? So we cannot just look at one destination address and say it goes to this VM. The second problem is that some of these machines might be what we call promiscuous. What does promiscuous means? Yeah. Promiscuous means they listen to all the traffic. All right? They are just, you can put on the Ethernet, and actually on the switch it is generally not possible, because on the switch you can just listen to all the traffic that is coming to your port. But if you have a switch which allows management, you could set a port to be promiscuous. Okay, so all the port traffic will go to that port, right? And so those things have to happen in this virtual environment as well. And for that reason we need these channels. So these channels are between the exit of the switches here, and we have a corresponding thing here, the entrance for them. So these exits of the switches are called V ports. The entries are called what? These are called VSI. Those are the those are virtual station interfaces. And these are the switch interfaces, virtual switch interfaces, including this one which is directly connected is a virtual switch interface. So basically these three have a corresponding image here, and so we need to decide here what goes where, and we send it on that channel. Okay, so and so that way not everything goes to everybody. Okay, that is why you need these S channels. S channels are the second layer of VLANs which limit the traffic to particular switch ports. Okay, and then we had this example where we saw that if the traffic is coming from this switch port, it goes to that here. That way all the traffic that is coming from here goes there and not to these other ports. Yeah.
So for this example, when the traffic is in the external switch, how does it know which port should it forward it to? How does it
on this side?
On the right side.
On this side?
Yeah.
Oh, that is basically, it will take up the VLAN and look at the MAC address and the VLAN of the inner thing, right? Okay. And then it will decide whether it goes out to the world or whether it goes back to the same host. So this is purely the standard VLAN MAC address forwarding.
So is it known that, for example, port E is responsible for VLAN's number?
Yeah, so this is known. Basically, everybody knows the VLAN membership. They learn it by, basically source learning. And so this knows that there is a port here which is blue and its MAC address is such and such, and actually even the VLAN blue. So that address, so based upon that address, it comes here.
Okay, so it means.
Yeah, and then it is encapsulated again in another VLAN, so it doesn't go anywhere else. It goes straight to this E, and then it goes out. Any question about this? So now the next thing is, how do we manage all these NICs? And this is very important today, because nowadays we have thousands of these things. I mean, if you have thousands servers, you have 10,000s of VMs. Right? Sometimes even millions of these things. So you cannot just go and program each one individually. There is no manual work at all in the data center anymore left. If there is a manual work, it is what we call orchestration. Everybody knows what is orchestration? What it means? Everybody knows what is an orchestra? You know what is an orchestra? You know, you go to a place where you listen to music and then that is an orchestra. Okay, so there is a director there who moves his hand like this and everybody changes their tune and they moves it like this and then like that and everybody changes the tune. That is orchestration. With one hand you could move 1,000 people. Right? So with one command you should be able to program 1,000 VMs. And so orchestration is done in the networking, and the way it is done is that there are standard profiles. So there are standard profiles which are, so we say, okay, this is profile type XYZ, just whatever name you want to, there's no IEEE standard, it's just, the provider standard. Okay? So they just keep them stored in the disk someplace and they say, okay, I need 10 of these, I need 20 of these, I need 5 here and 2 there and this and that, right? So those profiles, those are called network port profiles, they are applied to the VM. And a OVF package, now you know what is OVF. What is OVF?
File system.
Yeah, virtual file system. So that OVF, overlay virtual file system, or something like that, package is may or may not contain. So thing is, VM is created from OVFs. First of all, for each VM there is a disk that you just attach, give it to the server and say, okay, here it is. Start a Linux, start a VM, Windows 7, here, right? So those OVF files may not have the network profile in it. Because when the OVF were written, they didn't know what kind of network I will have. And after VM instantiation, generally the networking team applies a port profile to the VM. And now there are two different teams here again. There is a server team which knows all about the applications, and there is a networking team which knows all about networking. So the server team starts the VM and the networking team starts the network for that VM. So DTMF. So DTMF is data something management forum. Data task management forum. Actually, this is wrong. DMTF, I think it is. And DMTF will be data management task force. So if you go to the abbreviation list, it might be correct there in your handout. DMTF has extended OVF format, and they are the one who actually started the OVF format to begin with. They support the port profiles now. Okay? And that port profile includes resource allocation profile, resource capability profile, and vSwitch profile, etc., etc. It might say, well, I need a 10 gigabit Ethernet port on this, and that 10 gigabit Ethernet port should be on the blue VLAN, and that blue VLAN, whatever else you need to tell, about that switch, you just put that in that profile. All right, and this is how you get 10,000 blue VLANs, blue VLAN nodes, because you just give them all the same profile and they have the same color and everything else, and suddenly you have a VLAN all over the data center. Okay, so that is about the management part of these machines. Yeah. Okay, did I miss it again? Edge virtual bridge. Edge virtual bridge. Was VEB? Could be VEB. Virtual edge bridge.
It's the same thing.
Huh?
You're referring to the same thing.
I'm actually, so this is wrong. Basically, you can correct it to VEB management. But the thing is, this applies to VEPA as well. So it is not really specific to VEB. It is basically virtual bridge management. So maybe I should just remove the word E there. So,
EVB is used generally for both VEPA and VEPA. So this is right. EVB.
It includes VEPA as well?
VEPA and VEB. VEB is the technology, VEPA is the technology, and EVB is the...
Oh, I see. Edge virtual bridging.
Yeah.
All right. That makes sense. Okay, let me explain what he said. That the standard is 802.1 QBG, right? So either I could say 802.1 QBG management, which includes two different kinds of bridges, and it also called Edge Virtual Bridging. The name of the standard is Edge Virtual Bridging, EVB. Okay, so it makes sense now. EVB includes two things, BEB and VEPA, and also includes S-channel, by the way. S-channel is also in the same standard. And by the way, all these standards are available for free. For those of us who need them, we always keep them. I have all of these standards in my computer right here, and we read them, when needed, and when we need the authentic information, we read them. So you should get used to reading the standards. All right, so then there is auto discovery. There are lots of protocols for management, just like for OAM. For the carriers they made OAM. For the data centers they have protocols that allow the management, and we will not go into the detail except listing the names here so that you know that there are. So there is Edge Discovery and Configuration Protocol, EDCP. There is a VSI Discovery and Configuration Protocol. There is S-channel Discovery and Configuration Protocol, Edge Control Protocol to provide reliable delivery for VDP. Now VDP is the VSI Discovery. So let me just say a little bit, one sentence more about each of these. VSI Discovery. Basically we need to know how many ports are here on this side. Those are the VSIs. And so basically there is a protocol which says, okay, how many ports are there? Some switch asks some other switches that broadcast a request, and then somebody says, okay, I have 1, I have 2, I have 3, I have 4, I have 1, and then it adds up. That's the discovery. So there is a VSI discovery and configuration. Then it says, okay, all right, what, either they will themselves know that I am in the blue LAN, or they will say, okay, you are on the blue LAN now. Things like that, okay? Similarly, then there is a S-channel discovery, and there is a Edge Discovery and Configuration Protocol. So the Edge would most likely, and I cannot be sure, is vPort discovery. We need to know how many vPorts are there so we can set up the S-channel, things like that. So all of these discovery protocols are included there. And then, since this thing has to be very reliable and they don't want to use TCP, so they have their own transport protocol, which they don't call it transport, they call it ECP. They don't call it TCP, they call it ECP. But it has all the same features as TCP, which means it has windows, it has flow control, congestion control, three-way handshake, everything. But they don't want to. Can you understand why they don't want to use TCP? Anybody? Nobody knows? I think I explained last time. Because they are IEEE and TCP is IETF. So, so you cannot design layer 2 which depends upon somebody else. You want to have complete control over your layer. If suppose somebody doesn't have IP and they have Ethernet, what do they do? Right? So it's not political, it's just self-sufficiency in the sense that Ethernet is designed for all layer 3 protocols. For all layer 4 protocols, we cannot just depend upon one layer 4 protocol for anything, including the management. So they designed a reliable protocol for that. Alright? So now we move on to a totally different world. So this is all IEEE. IEEE is done. Any question about IEEE part? So now there is a third group of people who are working on the NICs. So there are two people. First, who make the NIC. Second, who make the switch. Sorry, people who make the hypervisor and the people who make the switch. Cisco versus VMware. And they came up with those alternatives that we discussed. But then there is something in between, which is the real NIC, which is made by Intel. What can Intel do in this business? And so they say, no, we have a solution which does not require you guys, and in their sense it is better. And so their solution is based upon PCIe. Now what is PCIe? All of your computers have PCIe, you know that, right? PCI Express bus. If you have a desktop, sometimes the port comes out and you can see it. If you have a laptop, the port doesn't come out in most of the laptops, but in some it does. But that's the bus, which is very high speed bus, which connects all the peripherals inside your computer, a CPU, to video, to storage, everything. Right? PCI stands for Peripheral Component Interconnect. And your Ethernet card actually goes on the same thing. So if you have an Ethernet port, it is connected to a PCI bus inside your computer. And it is designed by, not by IEEE, but it is designed by PCI Special Interest Group, which is called PCI SIG. And first there was a PCI, which actually I still have computers with PCI, but I can't find any cards for it because all the new cards are for PCIe, which is the latest version of PCI. PCI Express is serial point-to-point interconnect with multiple lanes, and you need 4 pins per lane. So you could, when you go and buy a PCIe card, which you can look up on Amazon, you will find 1 lane, 2 lane, 4 lane, 16 lanes. The more lanes you have, the more speed you can get. You can get up to 2 gigabytes per lane. Okay? And you can get up to 32 lanes. So 64 gigabytes. It doesn't go very far. It's a very short bus. But, and that's how you can get all these big speeds for very cheap prices. I mean, like I just bought a PCIe card probably for $10. And I don't know how many lanes it has, but I mean, for $10, you know, what can you get, right? So that is PCI Express. Now in the PCI Express, the way it works is that there is a root complex. In the next picture I will show you. There is a root complex and there are devices which we call them functions. So basically you put many devices, so you might have a video card, you might have a network card, you might have a disk on that same PCI bus. So the head of the bus is the root complex, which is generally near the CPU. The CPU is in charge. So that is the root complex, is the head of the function, head of the PCI, which is connected to the CPU. And then the physical function is their name for whatever is going on the PCI. So for example, Ethernet is a physical function. Another physical function, it could be video. All right. Now they have extended it so that they can do virtual functions. So you could have one physical PCI, but it could do many different, maybe thousands of virtual functions. So now you could have just one NIC card, but this will provide, without depending upon the hypervisor, without depending upon the external switch, this NIC will provide 1000 NICs. Okay, everybody understand this? So that is called single root IO virtualization, SR-IOV. Basically you might have, let's say in this example I have shown 2 functions. There is a fiber channel card and there is an Ethernet card. These are physical functions of those cards. But both of these cards are SR-IOV enabled, which means that they can provide you virtualization. So you can produce multiple virtual functions. These blue things are fiber channels and these yellow things are Ethernet. And there is single root hypervisor, which generally talks and keeps control of the physical resources, will keep track of the PF and tell them that okay, I need 2 VFs, and then connect the first one to this VM and connect the second one to this VM and so on and so forth, and then it gets out of the way. Once it creates those virtual functions, it gets out of the way, and then everything can go directly. So So this VM thinks I have a fiber channel card, and this VM thinks I have a fiber channel card, and so on and so forth. I mean Ethernet card, and they must basically use that. They just use those functions as if they were real functions. Yeah.
So a single root here means that there's the one single hardware.
There is one single hub here, right? In the next slide, I'm going to talk about multi-root. So just hold on to that thought. So the single root is basically you divide a card into multiple pieces, virtual pieces. All right. Any question about this one before I change to multi-root? It's simple. Basically, their NIC cards can do all of this that we were expecting the hypervisors to do and things like that, right? Hypervisor is still involved, but they're not really doing any function. There is no code there to do any of this. They just create they just tell the PF that you have to do this, and then they get out. So now PCI didn't stop there. PCI guys, just like Ethernet, just like fiber channel, they said, why do we have to be in every computer? And they have their own fabric. Fabric means their own network. And they said the advantage of using this fabric is that your computer can be cool in temperature and in price. And you could have this thing externally, and many computers can use it. Right? So here are your devices. You have one card, and I haven't put what kind of card it is. It could be fiber channel, it could be Ethernet, another fiber channel. This is all outside the box. So you have these blades, and on the blades you have these CPUs, physical CPUs, and now the cards are not going on the same place. They could be somewhere else, maybe in the next blade or in the next. Actually, don't go to the next rack, but maybe in the next level or something like that in the same rack. So these PCI devices are external and shared. So you save money. You don't have to buy that many cards. You could have 16 servers, but only 4 cards. And now, so you have these root complexes, which is in every machine. So there is 2 levels of virtualization here. These root complexes, and then these are called PCIe switch. These are not Ethernet switches. These are PCI. This is what is called PCI fabric, PCI network, right? So these devices are shared by these root complexes. And now you do the same game of IO virtualization. So now each VM can get whatever they want out of this available thing, and this doesn't have to be physical. Up to this point it is physical, but when you come to here it is virtual. You could have 4 physical devices and share with 15 physical servers without going any virtualization, because only 4 need it, other 12 don't need it right now. They don't need fiber channel maybe, right? But with virtualization, every virtual machine can get a piece of whatever they need. Yeah.
The switch is physical switch.
This switch is a physical switch. Yeah. Yeah, actually I have been clear about the dotted line here, correct. So the only thing dotted here is VM. And I haven't shown the VFs, but you understand, those cards will have lots of little virtual functions. All right, the world is going crazy with virtualization, if you are going crazy with virtualization. All right, everybody understands multi-root now? That you can have a smaller number of devices. So this is actually for saving energy and saving cost. It is saving energy because you are not heating up all the cards when they are not being necessary at that time. And you are saving, of course you are saving energy and saving cost because you are not needing that many cards. All right. So this, I think we are done with the VNIC part. Okay, there are 3 ways to do VNICs. VEB, VEPA, and SR-IOV. Actually, MR-IOV is also there. Okay, so 4 ways if you want to count that way, 4. One solution came from IEEE, one solution came from PCI SIG. Or 2 solutions came from PCI SIG and 2 from IEEE. Alright, so we are done with that. Now we go to totally different thing, is relocation, VM relocation. So remember we had talked about vMotion when we were talking about VMware products. And what does vMotion do? vMotion allows you to take a virtual machine and move it live when it is running to another computer. You don't have to stop the machine. You don't have to put it into hibernate mode. You just take it live and put it there. And so that means it has to have the same profile, same everything that it had on this machine, except the location has changed. So it has the same MAC address, same IP address, same VLAN, its new home. We need to extend the VLAN broadcast to this new home. So we need to make sure that the VLAN broadcast go to that position, that place. So after relocation, how does that happen? After relocation, VM sends a reverse ARP. I think we talked about this before. Did we talk about reverse ARP? No, maybe not. Okay. Reverse proxy was the thing that we had talked about. It sends a reverse ARP to all switches so that they learn its new location. So what is a reverse ARP? First of all, what is an ARP? Anybody knows what is an ARP? Yeah, and the reason is, if you don't know somebody's MAC address, but you know their IP address, you can ask the world. And this is a broadcast message. You send a broadcast message. Does anybody know the MAC address of this IP address? Alright? And anybody can respond. Whoever knows can respond. So that is ARP. ARP is address resolution, and we are resolving the MAC address. We know the IP, but we don't know the MAC, so we are resolving that. Reverse ARP is just the opposite. You didn't ask, but hello, please listen. My MAC address is so and so, or the MAC address of IP so and so is this. So you're just telling unsolicited everybody that this is the MAC address. Why you are telling everybody knows that already? You just had that MAC address a minute ago. But now the switches will learn that you are here. Right? Because that broadcast will go through all the switches, and the switches will know, oh, this MAC address was supposed to be on that port, now they are on this side. So that's the only way they learn is when you say something. If you don't say anything, they will think you are still there. So the first thing you do when you move is just say something. So everybody understand what is reverse ARP?
So it basically is just progressing the MAC address to the value of the.
Yeah. And it didn't have to do the reverse ARP. It could do any other broadcast. It will work equally well. Alright, reverse ARP. If a VM moves to a new data center to avoid tromboning. What is tromboning? So I skipped tromboning because it was in different part. I don't think I discussed it here, and I'm going to explain that in a minute. To avoid tromboning, a default gateway should be available at the new home. Tromboning. So let me see where I can explain you tromboning. Alright, I think this is a good picture to just explain tromboning. So let's say you have this one data center and you have this second data center. Right? Now you move from there to here. Your default gateway was here. Right? All the traffic that we are sending out of your network was going from here. Now you came here. So now what is happening is you are really very far from your default gateway. And so a lot of traffic is going to come to you, and then a lot of traffic is going to come to you from here for nothing, because you could have just gone out from here. If you had optimized this thing, there could be a gateway here that could help you. And in general, there are more than one gateway on the LAN, and you just select one because you don't want to confuse everybody. So you just use only one out of all the gateways that are there and use them as default gateway. Alright. So So this is called tromboning. Tromboning is basically, flipping back and forth for nothing. All right. And so these are the protocols which actually allow you to do that. First protocol is called HSRP, Hot Standby Router Protocol. So this is basically allows you to have multiple routers on the LAN, and one router is there and there is a standby router, hot standby. That is Cisco protocol. And VRRP is IETF version of the same thing. And VRRP is Virtual Router Redundancy Protocol. So basically it's same thing. You have two routers or multiple routers on the LAN, and one of them acts as the main and everybody else is sitting there standby. All right. So done. Now combining bridges. So all right, this is totally different topic. And I'm going to move totally different topic. Any question about VM relocation? None? Then we move to combining bridge. Yeah.
Now, if the VMs are moved geographically,
Yeah.
geographic apart servers, then appropriate bandwidth and necessary to move the.
Yeah, you have to do all that calculation before whether you can move it. I mean, you have to have first of all a cool CPU, because you don't want to make something which is hot already to hotter. So you do everything, all kinds of.
Goes into a cool CPU.
Cool CPU means in the sense that which is not overloaded.
Not overloaded, but it's still a working CPU.
Yeah, they're not turned off. Yeah, I mean, first thing you will do is turn on the CPU, put the hypervisor in it, right, and see, if you have just turned off some VM, maybe you can give space for this. So all that is done in the background. I mean, this is a big business by the management of the cloud. Companies, they are making products and tools for this, and Cloudera is a good example. And it's a big business right now, managing, orchestration is a big word. Believe it or not, orchestration is a big word in the industry today, nowadays. How to do 1,000 things at the same time, okay? Yeah.
The VIP, the last line is
Virtual IP.
the virtual IP is playing what role in the moving the.
Okay, so yeah, actually here, I think to be fair, basically this HSRP and VRRP slides I had in a previous lecture, which I had to remove because of the timing and other things. And I may get back to that later on, but basically the way both of these protocols work is that you have 5 routers and all of them have different IP addresses, just like they're supposed to have, but they also have a common VIP, right? However, they never respond to it. If somebody says, what is the MAC address of this VIP, they will not respond, otherwise 5 answers come back and will be very crazy, right? So only one who is master says, okay, here is my VIP address, this one, right? MAC address is this. So that VIP is basically the idea is that's how you get one router to all the traffic, is because that it has the MAC address. And then when that goes away, other routers come up, then they will say, oh, VIP, the MAC address for router is this, this VIP address is this, right? So now they become in charge. That's how it works. This is how those two protocols work. Remember we talked about this in ADC, that multiple servers can have the same VIP. They will have a real IP also, but they will have the same VIP. And only one will use it, right, and based upon the MAC address. Actually based upon the MAC address, the load balancer was sending it to the right place.
So what's the relationship it has with the default gateway?
Tromboning, yeah. So basically those two protocols are simply how to have a standby default gateway. When we say standby or virtual, that's what we mean. So you have, okay, and you might have more than one, okay. So what we are saying is that you will have one in this data center, one in that data center. And in this particular case where we are, if we move a VM from here to there is no reason for us to use this default gateway. Now we have to extend those protocols somehow so that we can use this data. When I am here, I can use my nearest one.
So just the standby one.
Yeah, multiple standbys here. So let me say one more time. See, when the VRRP and HSRP were designed, the LANs were so small. Right? At that time, they didn't think that people would be far away. But now that the LANs are 100 miles long, if I have 5 routers on this LAN, they're not all same equally good. Something which is 5 miles away is very different than something which is 100 miles away. Right? So now we really need more than one default gateway. You have a question? Nabun? Yeah? No? Okay. Just want to make sure. All right. Now we are going to different problem. Aggregation. So we talk about partitioning of bridges. You have one bridge and you want to partition it. Now we are going to combine the bridges. You have 100 bridges, I want to make one out of 100. If you remember my previous slide, virtualization is just two things. Virtualization is either partitioning or combining. Partitioning or aggregation. So we just finished the partitioning of a bridge. Now we see how to combine the bridges. And so here is the thing. If I have 100 bridges, I mean basically right now we need very big bridges, because the problem is now we have so many VMs, 10,000 VMs. Previously we used to have 32 port bridges and that was big. I never had a 32 port bridge. The biggest I ever had in my home was 16 port and that was big. But now these guys need 100 port bridges because there are so many VMs to connect to and so on and so forth, and they actually need 1,000 port bridges and 10,000 port bridges. So how do they make it? They take little bridges and combine them. And I will talk about 4 solutions in the next few slides. The first 2 are proprietary from Cisco, and the next 2 are the standard from IEEE. And I thought it might be okay. I mean, I don't basically. I mean, they're slightly different. But this is where they started. They started with those Cisco things, and then the industry liked it enough to make a standard thing so that everybody doesn't have to use Cisco technique or Cisco license or Cisco anything, right? So basically now there is industry standard. Actually, I think the first 3 are Cisco. Last one is standard. Okay? So let's talk about, First, this was not on the list, DVS. So VSS was on the list. DVS was not even on the list. So DVS is first solution. DVS is distributed virtual switch. And this came from VMware. And VMware said that we don't have to have vSwitch in every hypervisor. Or we could have VMs in a hypervisor, but the hypervisor could be virtual in the sense that the hypervisor could really be as if it is in every one hypervisor is in every machine. Okay, it is extending inside the machines. So that way, instead of having 500 vSwitch, we could just think of one vSwitch. Okay, which is connected to all these VMs. So they combined all their vSwitches into one virtual switch, which is called DVS. The virtual switch is distributed, some pieces in this machine, some pieces in that machine, some pieces in that machine. Now we can control the whole. We can control the whole environment, whole cloud by programming this virtual switch, this one switch.
Just
Yeah.
some clarification.
Sure.
You said one switch is divided into virtual switches which are distributed logically.
Okay. First of all, DVS is virtual, so it's not physical. There's no hardware in it. It's all software. Right? But basically, as far as you are concerned, you are the manager, you look at one switch and you say, well, this switch has 400 ports. All right? Port number 1 connected to VM number 1, port number 300 connected to VM number 300. So this is a big virtual switch. Instead of previously we had to say, machine number 10, port number 5 in that machine. Right now we have this big switch with all the ports connected to all these VMs.
So it is centralized
This is centralized. Now you see why centralized is coming in. Is because, I mean, obviously you could have, standby and all that, but this centralization is the key word right now in the industry. Everything is getting centralized because you cannot do 10,000 distributed things. If you have 10 things, you can do distributed. All right? OSPF, BGP, everything works with 10, 15, 20 things, but it doesn't work with 10,000 and a million things. Right? So distributed stuff is, see, this is the difference. Original internet was designed to be distributed because we had centralized network in those days. The current internet is designed to be centralized because we have distributed and that doesn't work. At least not in the control plane. So this is a centralized controller which many physical hosts. DBS couples the control, and so now this is where the decoupling of the data and control plane is started. So they decouple the control and the data plane of the switch so that each VM has a virtual data plane, virtual Ethernet module, but it is managed by the centralized control module. So what that means is that the forwarding table comes from this central place. It tells you, look, if you get a packet from VM1, it is going to packet VM5, send it this way. If it is going to send 3, so whole forwarding table in the switch is not learned, divided, and it is just done from this central place. That is DVS, right? Appears like a single distributed virtual switch, allows simultaneous creation of port groups on multiple PMs. And on this switch, you could say, well, I need 100 more ports. 5 on this machine, 10 on this machine, 3 on this machine. Right? And provides an API so that other networking vendors can manage vSwitch and vNix. And now everybody, when they do something like this, which is like their proprietary, they make sure that everybody else follows them. So they made a standard API, so everybody else can do it. Everybody else is following. Cisco is following. HP is following VMware. And that.
So
Yeah.
Is that implemented only one single physical network and NIC?
No, it could be in a computer sitting in the central office.
It's like server.
It is a management station.
Between the virtual machine.
It could be a virtual machine in a server too. I mean, it doesn't matter how it is implemented, but it is controlling all the ports. The thing is, this is not physical hardware. This is not something that you have to go and buy. Yeah, you have to buy it from VMware, but all they send you is a disk. Do you understand? Does it answer your question?
Yeah.
Okay. All right, so this is DVS. You already see that DVS is basically aggregating all the vSwitches and making it look like one. Well, Cisco went one step ahead. They said, why don't we take physical switches and make them look like one? All right, and that is called VSS. Virtual switching system. You can take 2 physical switch and let them look like one virtual switch. Okay. Now this is again a thing which is industry wide, but the name is different. This name belongs to Cisco. Other companies like Enterasys has virtual switch bonding, and every company has their own name, so I don't want to confuse it too much. But this is implemented in the firmware. So basically these switches have to be modified to be able to do this. All right, and basically what it is now they have one control plane. Only one control plane is active, and the data plane capacity is doubled. So whether you send the switch 10 gigabit here and 10 gigabit here, you can get total 20 gigabit coming in. As shown here, there are 4 links of 40 gigabits coming in. Okay, and they look like going to one switch. And both switches are kept in sync. So there is a link in between them, and they are kept in sync to enable inter-chassis stateful switch over. You know what that means? Stateful means both switches know exactly what the tables are, where traffics are going, and everything else. The whole state is in both the switches at the same time. And switch over. So if this switch fails, this one can take over the whole thing. Now what will happen is though, these 20 gigabit will not get there because this switch has failed. But whatever is coming in will go to the right place. Generally both of these links will be going to the same host anyway, as shown in the next picture. So generally what you do is you take a switch or a host or whatever that is and connect them to two switches. Alright? And if they are going to one switch, then you make a link, what we call link aggregation. Right? So if you have three links going to one switch, you make a link aggregation, which we call link aggregation control protocol in IEEE, but in Cisco terminology it is called port channel. Port channel was before IEEE did this, so that is the original name, VPC. Not PC so far, but port channel. And now you can take two which are going to different switches. The switches can become one and this can become VPC. Virtual port channel. So what it is that you have one 20 gigabit link going out from this thing which is physical as shown but could be virtual as well to this thing which is virtual. Okay, so this is a virtual. Now what the advantage of this is, obviously as you know, is in the spanning tree. If you are using still a spanning tree, for a spanning tree these two links will be blocked. With this one both the links are active because there is only one link here. Alright, and generally you will have two links going from this switch to two switches here, two links going from this switch to two switches here, and then there will be, instead of doing that, it will look like this to the spanning tree and all the links will be used. Yeah.
As a previously we have learned that LACP something
Yeah.
Link
Aggregation control program, yeah.
What was it related to this?
Okay, so this is link aggregation. The only thing is IEEE did not define this kind of combination. Okay, so the link aggregation is same as port channel. You can go from one physical to one physical. Alright? And IEEE did not say that you cannot do this, because if you make this one virtual, then this is link aggregation. Right? From physical to one virtual. So actually, so the difference between LACP and here is that now we are combining the bridges into one. Virtual bridging was not there when this thing was. So as we go to the last slide, IEEE has come around and allows this. But when this thing was done, VPC and VSS was done, at that time there was no IEEE standard. Oh, they had the standard for LACP, but they did not have this whole combining the bridges thing. So what is new here is combining the bridges, combining physical bridges into one virtual bridge. Yeah.
Does this virtual force channel make this one virtual switch have one priority, because they were both two physical devices?
Yeah.
With two MAC addresses, two priority levels.
Yeah, MAC addresses are still there. Let me tell you, MAC address do not belong to this switch. MAC address belong to the interface, to the port. Still, the number of ports has not changed. For example, there are 3 MAC addresses here.
MAC addresses will be there.
Yeah.
To make this work like this, for aggregating rather than blocking off channels,
Yeah.
This switch should have one single priority. Otherwise, both switches inside will be...
Okay, now again let me clarify. Priority does not belong to the port. Priority belongs to the traffic. Alright, so having said that, when they advertise as one link. So when they send out a spanning tree message, they will say, I have a link of 20 gigabit to that switch.
But when route is nominated...
Yeah, the route will be nominated based upon the distance. So everybody who is here, they would rather take a 20 gigabit than a 10 gigabit.
So for that purpose, this acts just as a
one link, yeah.
Switch and
one switch and one link, yeah.
switch and one.
Yeah, that's why the links are not blocked. All right. Okay. So actually, I switched this slide and then I was trying to explain. So I was trying to explain first two concepts. First concept is virtual switch system, which means you can take two switches and make them one. And second thing is virtual port channel, VPC, which means that you can take the links going to two switches and make them look like one. Okay? So this is VPC, and before that was PC was port channel. Now this is virtual port channel. So this combined switch is called VPC domain. Each member of the VPC domain is called VPC peer, so there are two peers. And VPC peer link, which is the link between them, is used to synchronize, which as before. And all learned address step cable are kept synchronized among the peers, and one peer learns it and the other sends it to the other one else. Anyway, so you could have more than two also, right? So this is what basically it is, that you can combine as many switches as you want, and the links you can combine them. Once the switch gets combined, you can combine the links. Alright, and that is called virtual port channel. And this term is used so much in the industry that you really need to know this term, and that's why that was one reason that I put this slide here, even though IEEE has something else. But DVS, distributed virtual switch, throughout the industry. UPC, VPC throughout the industry. BSS, so I mean, like BSS may not be that popular, but VPC is. So you really need to know these terms. VPC allows aggregation of links going to different switches. STP does not block links, all capacity are used. Unlike BSS, maintains two independent control planes. Independent control plane means in-service upgrade. So basically what it is when you do VPC, there is a little bit more than the VSS, and this is a fine point, technical point, and if I wish I can explain it, but I'm going to try to explain to it, is that in the other case, one switch basically doesn't learn anything, doesn't do anything. In this case, it also learns, it has control plane and it synchronizes with the other one, but it allows you to do in-service upgrade. So you could take out one switch and then you don't have to take any service off. Anyway, so this is a little bit difficult to explain, but anyway, let's move on to the next issue, which is the fast back to STP, which means that if when you take out one switch, then it is like STP. Then this switch has to announce that I have two links and so on and so forth. And so it's fast back to STP. So it is not really used for very large domains. Large domains means 1,000 port switches are combining 1,500 switches or combining 5 switches. It's small, maybe 2, 4, 3 switches. Okay. VPC is Cisco proprietary, but other vendors have similar technologies. E.g. SMLT by Nortel. Nortel is no longer there. Multi-chassis link aggregation, MC-lag by Alcatel, but there is no standard yet, even today. It's all being used, but not having no standard. Then, one more technology which came from Cisco is fabric extender. And this is getting even closer to combining. Basically, what they did was they put some really simple boxes called fabric extender that didn't have very high powered CPUs. All it had was very simple ports, just like your home ports, very cheap, very simple ports, but they were controlled by a parent switch which had a very high powered CPU and could manage 1,000 ports. Alright, so you buy a very high powered switch and you buy lots of cheap these fabric extenders, and then you can make a big switch with lots of ports. Alright, FEX consists of ports that are managed by a central remote parent. L2 fabric extenders, which are 48 host ports, you can buy these extended 48 ports, connected to a parent switch via 4 to 16 10 gigabit interfaces. So you could have 4 to 16 uplinks here. Parent switch provide a virtual switch with 576 ports. So you see how do you get 576? You have 48 host port, 48 ports here per fabric, right? And then you connect to 16. Parent switch has 16. 16 times 48 is 576. Okay, this is called chassis virtualization. Chassis virtualization because we have physical chassis which is separate. Everything is physical here, by the way. You do have 576 physical ports where you can plug in, right? But they're not in the same chassis.
Here is the fabric channel.
Oh, there is no fiber channel. Okay, all right. The word fabric started from fiber channel. but we already used it in PCIe fabric and now Ethernet fabric. So basically the fabric term has come from fiber channel to all the networking technologies. So we say network fabric, when we say Ethernet fabric, we mean exactly Ethernet network. There is no fiber channel. Alright, so this is chassis virtualization. All software updates, management, forwarding, control plane is managed by the parent switch. So these guys are very simple. Alright, and a FEX can have an active and a standby parent. So if you don't like one parent, you can have two parents. Okay, I think I should stop right here.